Welcome to today's webinar. The topic today is optimization with stress and strain analysis. My name is Andreas Hörold. I'm responsible for marketing and PR in the company Dlubal Software. For instance, the German and English webinars, the technical content of the website, newsletters, customer projects, and so on. I will be the moderator today, and I will answer your questions during the webinar. My colleague Florian Hiddemann will be the presenter. He is responsible for the product development of RFEM, for the add-on optimization and costs, and for the Dlubal API. Okay, that's all for the introduction. I say something how you can ask questions, at least for the attendees who participate the first time. I switch off my webcam that you can see the full screen. Just press the button with the question mark, then enter your question in that field, present, and I will receive your question and I will answer you. And the other possibility is to watch the entire webinar and then email questions to info@dlubal.com. Okay, that's for the moment all from my side. I hand over to Florian. Florian, you can start.
Thank you, Andreas, for the nice introduction, and welcome to this webinar regarding some optimization together with the add-on stress-strain analysis. What I would like to show you today is a small model here where we want to optimize the geometry, in particular the plate thicknesses and the length of this plate here. In the first step, we only play around with the plate thicknesses, and the second model will include also some changes in the whole geometry of this plate as well. This will be the only model we have a look into today. I would like to show you the basic initialization, the setup for the add-on optimization, how it's worked together with the stress-strain analysis. We do some design setup here as well. And I would like to point out some nice details here in this model. For example, how to properly model some screw connections, or to get a more realistic result regarding here applying the loads on some holes like this, and have a backend plate with a non-linear support for the surface. So just to walk you through the model we are looking for today, the overall goal is to find a geometry which fulfill all our specified design needs and to achieve the minimum weight of the whole construction. So we just assume it's a facade connector or anything like that, and we would like to improve the material costs here for several of these connectors. Let's start with the loading. Here are three simple load cases defined. The combination wizards are turned off. We only need for this small example a design situation which contains some loads and design criteria we use in the design add-on. And we have here tension, vertical and horizontal force, just as other actions. And the forces here are applied on this single node behind the dimensioning. Let's turn off this for a moment that you can see it here. There is node number 10, and we apply a tension force in this direction in load case 1. In the second load case, we have a vertical force and a horizontal one, which will bend this plate here around the weak axis. So how is the model working? As you might see here, we have some nonlinear members here. And if I activate the transparent model, you can see that these try to simulate some weak beam section here. The model dimensions for these beam elements are chosen in a way that the surface area of the connecting part for the beam end is the same like the area for the cylindrical surface inside of this model here. So if we just make them invisible, show the transparent model, Then I choose a surface here where you can calculate with the diameter and P the surface of the cylindrical area, and then model some beam elements which would have the same area here. We made some good, this is our recommendation how to model this kind of screw connection here to have some effects regarding displacement of the hole itself and let the force find its way into the connecting plate here. Around the structure, there is a mesh refinement. So we would like to see a finer and nicer mesh in this area. Here is a radial node mesh refinement defined, circular. And even if this is bigger than the connecting plate, you can see that we have a nice structure for the mesh. On the plates itself, there are also defined some mesh refinements which make smaller elements, just to ensure that we have a good looking, good distributed fine net here. The same is done with the holes in the plate, which models the screw connection to the building here. There's a circular node mesh refinement with the same settings like we saw before. And the whole backend plate is supported with a nonlinear surface support. This is just to give a more interesting example. If you have like concrete under it or a filler or whatever, and it's modeled with failure in a negative contact thread, so we only can transfer positive pressure forces. And we are free in both lateral directions. Connecting to the center of these holes here, there are beams with a round diameter of 40 millimeters. In this simple example, they just represent some dowels or anything which are connected into the building and they are filled out with glue or something. I'm sure in your project you have the right and correct assumptions for that. And they are also supported all around to restrict the movement here with a spring constant that also simulates some bonding inside the first 80 millimeters of this connection. So it's a small example here. These are millimeters. We have these dimensioning here to get an idea what we are talking about. Okay, and to get a feeling for the system behavior, let's just calculate for now the static analysis. And after that, we will set up the stress strain add-on. So if we have a look on the deformations, you can see we are pulling with the tension load case here and the hole is deforming as well. It seems that we apply pressure only on this side of the hole like we intend. And the plate here is obviously deforming in a way that we can expect some contact stresses here, which would add some small forces to the bars. We can see this as well. If we pull with 1 kilonewton here in this direction, we get 0.26 in each bar. So it's a symmetrical load, but a little bit higher than expected. And maybe you can see this in the contact stresses. Here on the edges, because of the plate deformation, you get additional forces due to the fact that the band and plate is leaning against the building and apply another lever arm, let's say, on the bars here as well. So it's a little bit more interesting. And in vertical direction, we can see we have pressure forces here on the bottom side. Here on the upper part, there it's free, it's a nonlinearity. And if we bend it on one side, horizontal, we also see this in the bolt normal forces. And if we switch on equivalent stresses for the plates, you might see that we are dealing with a logical system here. Okay, and what do we do now to add some criteria to dimension it properly? In the stress-strain analysis, we have several options to define limits, and we start with the surface configuration. Because we have defined some material here, we make use of the parameters in our material library. So the add-on for stress-strain analysis will use the parameters from the material and limit normal stresses like they are described here in these formulas. What is important to know that the design add-on here uses totally different results in the static analysis. So if you limit sigma 1, sigma 2, and for example here this equivalent, it might have the same results also in the static analysis, but it's calculated on the own design checks defined here on the right side. So if you have sigma 1, for example, you can check here what is calculated behind. And if you want to have a user-defined limit for this, you can also input your absolute value you want to use for this, or you define a user-defined factor. If you don't want to design for 1.0, you can, for example, also restrict this to 90% of the allowed limit here, according to the used material. So you are free to edit these values here. By default, they are mostly according to your standard and code you have defined in the background. You can even change the factor here if you want to multiply that by 2 to see, okay, you allow double time of the allowed value. You can do that as well. But here in the default state, we check these parameters, and these are then in the following criteria to say this is a valid or not valid result. This is important for the optimization algorithm later. We also defined a line weld joint, and in the model, we can see it here. It's defined between both of these plates. Just makes it a little bit more interesting here. It's a T-joint, double fillet, and the weld size uses the global parameter we've seen before. It's half of the measure of the plate thickness. So on both sides, you have 6 millimeters for the weld joint here. And there's also a stress strain analysis. And maybe you know this article from our knowledge base. It's also available in an English version, but here you can see we have some article here how to calculate and design check such joints. And according to that, I calculated, you can also find it in Eurocode, the stress limits I will make use here. At the moment, this line welded joint doesn't take it automatically from a material and makes these assumptions. So you have to calculate them on your own and define them as user-defined limit stresses. If I do it for material class S355, you can see that we have 436 for the comparable Mises stress, and for the normal forces in direction of the backend plate, and we use the 353. Also, last configuration is about the beams here. You can also activate these beams, and I will show you this in the example. If you switch here to the stress strain analysis, and obviously we don't want to calculate all these other members we have here because they are only to model the forces on the plate. Yeah, we can have a look on them. These have a non-linearity and they fail if they got tension forces. So they only apply pressure forces and have a custom flat cross-section. And we don't want to have them in the stress strain analysis, but we would like to see the other members. And you can go just to the input data and define the objects where we want to analyze them. So I just manually select these 4 members. And now you can see here, we saw sections, and we also have now the sections here and member configurations. In the member configuration, there are a lot of different options to edit the limit stresses, the limit normal stresses here. And we just go for the standards, which make use of the material parameters, but obviously you can use a lot more information here. So for now, let's see how the system reacts. If we calculate the stresses now with the current configuration, let's see what happens. We go to the stress strain analysis, to the governing results, and see, yeah, this would work. We have a valid result, but maybe this isn't the optimal configuration. So how do we go with this? How do we find an optimal dimensioning goal? Just to remember, we have the global parameters here defined, which we make use of. So everything what is a global parameter can be used for optimization. And if you do it like you do it without add-on optimization, you have the ability to define these as a value. But if you have the add-on optimization activated, you can define these as an optimization type. And we make the simple version today. We go not for ascending, descending options. It's just optimization. And then here on the right side, there appears the optimization parameters. You can define for each parameter the minimum, the maximum value, and increments and steps here. So in total, we would have seven states for this variable, which we want to try out, and 7 states for the other one, including the minimum and max value. Under the menu for calculation, you can find the optimization settings now. And in the optimization settings, on the right side, you see exactly these global parameters which are set to optimization. And here you can also define later on if you want to make use of them, if you want to vary them in the way you specified with minimum, maximum, and the steps in between. And this has an influence on the number of possible mutations. If we see we have 7 states for the plate thickness A and 7 for B, we come to 7 with 49 possible model variations. And in this dialog, we set the overall goal, the target value. This is one of the most important settings here. There are as well some other options here, and in the future we would like to add also some formula-based evaluations or some other result types to give you more flexibility regarding your optimization goal. But at the moment, these are in a state of internal concepts right now. So for now, for today, we optimize for a minimum total weight of the construction. And for the first example, I would like to use the optimizer all mutations. This is just it's a dump method that varies all possible states. And the clever part of this add-on, I show you this later on, are the algorithms we can make use of, which try to follow more scientific strategy to find the best possible parameter settings in the shortest amount of time, let's say. So for now, let's calculate with all mutations. And what is important, every time you want to make use of such an optimization run, you have to set it active here. If you calculate now and reopen the dialog again, this will be deactivated. It's a mechanism that tries to avoid unwanted calculation runs one after another. So what will happen now? We won't calculate all 49 possible mutations because we have some clever strategy inside this model here as well. In the background, it will now try to calculate the models until it finds the best valid one. What the add-on optimization does now is verifying our two parameters, and it evaluates with the target value here. The red exclamation mark means that our activated design add-on has at least one design check which not fulfills the design limits. So if any design check exceeds 1.0 or whatever is defined there, a red exclamation mark shows that this is not a valid result. If we found a valid result, it will be a green arrow, a green check. And there is also a third option which we show, which we'll see in a few seconds, because we try to save time here. Now we have just a calculation with all possible mutations, but soon we will see that with a special combination here in this example, we will have a valid result. And then something happens I would like to show you. This is kind of an internal improvement here. We see that no combination with plate thickness of 8 mm here leads to a valid result, but now we have 10, 10 as a valid combination, and suddenly we jump to the end of the calculation run without calculating 30 variants more. Why is this the case? You can see here that there's also a blue marking which say, okay, these are not calculated. The optimization add-on found model number 9 with 4.2 kilograms as a valid result. And it calculates in the background what was alone from the geometry. If you take this geometry here, you can calculate without calculating the RFEM results by stresses, design add-on, whatever else. You can also say, okay, these parameters here will lead to a weight of the construction of 5.4 kilogram or 7.0 kilogram. And since all these results would be, would not so good as our model number 9, we skip the calculation of the design add-on here. So it saves a lot of time until there is a possible mutation which would lead to a better weight than 4.2. And since this is not the case, because everything what could better than 4.2 was already calculated as not valid, we skip these here and have the best one in the result. So we can check in the stress strain analysis and see in the governing results we have around 90% as a maximum usage, and we found the combination 10 to 10 for the plate thicknesses. And this includes the evaluation for the members here for these 4 bolts. It includes the stresses which are set with sigma 1, sigma 2, and the von Mises equivalent stress, as well as our custom defined stresses in the line weld. So that's it. The add-on gives feedback to the add-on optimization, what is valid, what is not valid, and varies these results. And with 49 possible mutations, it's affordable to just have a look at all of them, but it gets a little bit more tricky if you have further parameters. And now we are enhancing our example here, and later on we compare this with the pre-calculated version here. So what we want to do now is also make some variation for this part. I already measured it. For this length here for the plate where the load is applied. Therefore, we go to the global parameters, make a new optimization variable, because this is the one we want to find in this small example, and we verify it from 80 to, let's say, 140 with steps of 10. So it tries to help me here with some assumptions. Sometimes you have to move back and forth because it's calculating 6 by 10 and then the end or beginning value. And as you can see, we have now a third variable here. And with this variable, maybe you already know, you can use these formulas directly into some coordinates or other input fields. And just to demonstrate that it's also possible here, we can use a formula directly in the global parameters, calculate some coordinates here. That's half of this length. And now I use them here as the z coordinate for this node. So this is the upper part. And also for the lower part. Okay, and now we have another option here. And if you change this value, we can see this directly affects the model. And of course, with a lot of fantasy, you can build some more or less very complicated models with formulas and calculations. Volumetric bodies, which are constant geometry, etc., whatever you might want to model. For this small example here, just gives another variation. So if we go back now and want to optimize this, we see, if we want to calculate all possible mutations, we have 343. And this might be a lot. And if you add another parameter or make smaller steps, let's say 5 millimeters, it's getting bigger and bigger. Let's just do it here in this example. We say, let's do an increment of 5 millimeters up to 150. And we have 700 mutations. Yeah, and if you have a fourth parameter like material, cross-section, you can optimize with a lot of different parameters here. It explodes very fast, that you have thousands of different mutations. And we have some strategies built in for this reason. If you choose for such kind of problem, the particle swarm is very convenient. If you activate this, you can limit the maximum calculated percent of these mutations. So if we would go for 5% of the mutations, we will calculate 5% of 735. And let's do this right now. So the algorithm won't just go stupid, holding one variable fixed value and then counting the other up. It has a look on the sensitivity for each parameter, which leads to a valid result with an optimized target value. And here, luckily, with the random mutation, it found a result, but we already know this can be much better. And the algorithm is trying to find with mathematical and scientific strategies behind the best mutation in a short amount of time. And it will, at a maximum, calculate 36 models now because we set it up to 5%. If we have, like we show in the first example, some models which exceed the best optimization goal from this run, we will skip the calculation, which makes it even faster. So the 36 combinations here are also quite fast now. And we already found with varying this length, a much better system than before, where 8 and 8 is also possible. So what is special, what is nice to show you and demonstrate here? If we go back now and we have calculated results into the dialog for optimization settings, we see here some sensitivity factors. And these sensitivity factors represent the influence of this variable to an optimization goal. So this parameter for the plate thickness B, is more sensitive to the target value and the valid result than the length of the plate here, according to all mutations calculated up to this point. And we built in, it's not easy to understand, we have to admit, but if you activate the pre-calculation of sensitivity factors, RFEM will do a two-step calculation to achieve more refined sensitivity factors here. In the first step, it calculates an amount of, if you make the k factor 2, 60 possible mutations. Then the add-on has some sensitivity factors. And after that, an optimization one will be done only if some variables have a sensitivity greater than this value. Alternatively, you can choose the number of parameters with the highest sensitivity factor. For example, if we would calculate this one, RFEM will go with another run for 60 mutations, re-evaluate the sensitivity factors by 60 mutations then, and after this it will make a optimization run with 5% of 735 and combines the two best parameters, which would be from this execution B and A for the plate thickness. So this is this option here you can see below. It's very handy if you have a lot of different parameters, maybe 100, 400,000 possible mutations, and you want to have more control. And if you have some models which need a lot of time to calculate, you are happy if you can reduce any amount of possible mutations you would like to see. Another big thing is that our results are stored now in cache. We made our first optimization run and we have some results here. And if we start another optimization run here, for example, with 20% of the mutations, and I leave that as it is, start the calculation again, then we can see that our existing results are stored in the meantime. So they are not deleted, and the number we need to calculate is reduced. So you have the advantage that you can, if you have intense calculation jobs, you can just store these models and calculate them later on if you have no changes in between with the model itself. And you can abort the calculation as well at every time. And we store the best calculation you find up to this point. So you can see we have model number 11. And if you click any other combination here and you want to see what would the result be, for example, model number 20, just make a double click here and you can see that RFEM is setting the parameters like they are used here. And then you can calculate this current case. You won't start another calculation optimization run here because it deactivates after each use. And then we see the results in model number 20. Okay, you might see it would be valid, but also with a very high target value. So this is not considered as an optimization goal, an optimized goal. And these ones here are calculated because only the next variants which have less weight than 3.5 will be calculated then. And yeah, now we had some very good options here, and we saw that we found even with the 5 millimeters, that is a better optimization one than in my prepared model here. And for today's webinar, the short one, that was everything I would like to show you. And thank you very much for your attendance. And I give back to Andreas for the moderation right now. So thank you very much. And if you have any further questions, please write us after the webinar. Thank you.
Thank you, Florian, for your presentation. I have an additional hint. You can book our online courses, for example, the RFEM 6 Masterclass course. It's a course for beginners. Then the Eurocode 2 course for the reinforced concrete design. The Eurocode 3 course for the steel design. The Eurocode 5 course for the timber design. And the Eurocode 8 course for the earthquake design. For more information and prices, you can scan the QR codes in the middle, or you can click at the links here. You can download the slides, the provided models, and the recording from our website. In the next days, you will get an email with a link to that website and also a link to your attendee certificate. Okay, that should be also all from my side. I thank you for your attention. Thanks to Florian for the presentation. I wish all a nice rest of the day. I hope we meet each other in a future webinar. Bye-bye.